focus our discussion on finding the volume by integration. And first, we will consider the volume of solid of revolution. Now, what is meant by solid of revolution? Now, actually, initially, we do not have a solid. What we have are plane region, okay, on a plane, okay, of course, on a plane, and the line that lies in the same plane as the region. And we call that line as the axis of revolution, or sometimes we call it as axis of rotation. So how do we form the solid of revolution? So let us consider a rectangular plane here, and let this horizontal line be the axis of revolution. Now, imagine rotating this rectangular plane about the axis of revolution. We can actually form a right circular cylinder if we will rotate this rectangular plane region about the axis of revolution. Now, on the other hand, if we have a semicircle, rotating it about the axis of revolution can form a sphere, a solid sphere. And if we have a right triangle revolve about the axis of revolution, we can form a right circular uh, cone. Now, look at the last figure here, last plane region. Now, what is the difference uh, of this plane region from the rest? Okay, now take note that this rectangular plane does not touch the axis of revolution, unlike the first three figures in which the plane region touches the axis of revolution. Here, the rectangle does not touch the axis of revolution. Of course, if we are going to revolve this about the axis of revolution, which does not form part of the plane region, then it will also form a circular cone, but it is hollowed right circular cylinder. Okay, uh, the space here between the bottom or the lower part of the rectangle and the axis of revolution when revolve about the x-axis will form this hollow space. So we have a right circular cylinder. So in our discussion, we will focus on finding the volume of solid of revolution using integration. And how do we do it? We will consider three methods, okay? The first method of which is the disk method. The second method is what we call as the ring, or sometimes we call this as the washer method. And the third one is the cylindrical shell method. Okay, and first we will consider the disk method. Now, in finding the volume of solid of revolution using the disk method, there are two things that we must consider. First, the plane region must touch the axis of rotation. So, if we will consider the x-axis as the axis of rotation, we will consider the region R touching the axis of rotation, which is the x-axis. So first, the region or the plane region must touch the axis of rotation. Second, the element must be perpendicular to the axis of rotation. So let us write here, the region R touches the axis of rotation or revolution. And second requirement, the element is perpendicular to the axis of rotation. So let us consider a function f which is continuous within the closed interval from a to b. Okay, so let it be continuous and non-negative on the closed interval from a to b. And we will let the region R be the region that is bounded above by y is equal to f of x, this blue curve, below by the x-axis, and on the left by x is equal to a, on the right by x is equal to b. So we will consider this plane region. Now, try also imagining that we will divide this region R into rectangles. So we will consider infinitely many rectangles, which are the subdivision of the region R, and we are going to represent the rectangles by this element, the rectangular element. Now, since we will use the disk method, okay, the first condition is satisfied. The region R touches the axis of rotation, which is the x-axis, and the element must be perpendicular to the axis of rotation. It is perpendicular to the x-axis. Okay, so just imagine also revolving this region R about the x-axis. If we will revolve this region R about the x-axis, then this solid is formed. And if we will focus on the rectangular element, which is perpendicular to the x-axis, okay, to the axis of revolution, and it touches, of course, the x-axis, we can form a circular disc. Okay, this is the circular disc. Of course, we can find the volume of the circular disc. And since we have infinitely many rectangles revolve about the x-axis, then we have infinitely many circular discs. And if we will get the summation of the volume of the circular disc, then that gives us the volume of solid of revolution. We will have the Riemann sum. And the Riemann, if we have the Riemann sum, we have the Riemann's integral. And the Riemann's integral, of course, is the summation of, Riemann's sum, of course, is the summation of the sum of the circular, sum of the volume of the circular disc. And if we will get the limit as the maximum delta x approach zero, then that will give us the Riemann integral. The integral of the volume of the disk, the representative disk, okay, and limit will go from the lower limit a to the upper limit b. It will be evaluated, the integral will be evaluated within the closed interval from a to b. Okay, so for the first method, the disk method, okay, we have to consider, of course, the volume of the disk, and for the disk, the volume is computed by using the formula pi r squared times the thickness. If we will let r be the radius of the disk and delta h is the thickness, if we have, say, this disk. Okay, let us consider this disc. Of course, this is very, very thin. Okay. We have a circular disc. The center of the disc is here. and we will consider the radius r, and this is the thickness delta H. So the volume of the disk is equal to the uh, area of this surface, okay, the base, times the height, which is equal to the thickness. So volume of the disk is equal to pi r squared times the thickness delta H. So since y is equal to a function of x, then we are going to replace r by y, which is equal to f of x. And the thickness is delta h. And here, the thickness is the differential of x since the element is perpendicular to the axis of revolution. And the radius r is equal to y. So if we have this element, the circular disc, the radius of the circular disc is actually the length of the element. So the length of the element is y, which is equal to f of x, and the thickness is the differential of x. So the volume is equal to pi times the radius square times the thickness, and we will evaluate the limit, the integral from the lower limit a to the upper limit b. Now, on the other hand, if we will consider the axis of revolution this time as the y-axis, then if we will use again the this method, if we have this region R bounded on the right by x is equal to a function of y, and on the left by the y-axis, okay, below by y is equal to c, and above by y is equal to d. So we are actually considering the closed interval from a to b, and the the condition here is the function is continuous and non-negative within the closed interval from C to D. Now, this time, since the axis of revolution is the y-axis, then the element must be a horizontal element. Take note that the horizontal element is perpendicular to the axis of revolution. Now, if we are going to rotate the region, the plane region R about the axis of revolution, which is the y-axis, we can form this solid. Again, we will consider this rectangular element revolve about the axis of revolution, okay, which will give us a disk. This time, the radius of the disk is the distance from the axis of revolution to this point on the curve. That is actually the length of the rectangular element. The radius is equal to the length of the rectangular element, and the thickness of the disk is equal to the differential of y. So again, by using the formula for volume of the circular disk, volume is equal to pi r squared times the thickness. This time r is equal to x, where x is a function of y and the thickness is the differential of y. Hence, the volume is equal to the integral of pi times x, which is a function of y raised to the second power times the thickness dy. And we need to evaluate the integral from the lower limit c to the upper limit d. Okay, so we had actually two cases where the x-axis is the axis of revolution, and in this case, the axis of revolution is the y-axis. But it is not only the x-axis nor the y-axis which can be considered as the axis of revolution in using the disk method. Now, as long as the region touches the axis of revolution, which can be any horizontal line or any vertical line, as long as the region R touches the axis of revolution and the element is perpendicular to the axis of revolution, then we are considering the disk method. So this time we will consider solving the examples for this method, but this time we are going to use the whiteboard. So I prefer using the whiteboard in discussing the solution of the examples. And you can also find the solution of the different examples for the list method. Okay, but it is not shown here how to draw the curve or how to draw the region R. So what we will do is to sketch the region R also before we find the volume of solid of revolution using the disk method. So I'm going to stop sharing the lecture. And in the first example, we are going to find the volume of solid of revolution generated by revolving about the x-axis, the region bounded by the curve y is equal to square root of x is equal to 4, and the x-axis. So to sketch the region, we need to consider the curve y is equal to square root of x and x is equal to 4. So to find the point of intersection, point or points of intersection, we have to solve the two equations simultaneously. So we will consider the system consisting of the equations y is equal to square root of x and x is equal to 4. Of course, x is equal to 4 is a vertical line, no? And what about y is equal to square root of x, no? To easily comprehend, okay? If we are going to consider y is equal to square root of x, okay, this is actually one of the roots from the equation y square is equal to x. Now take note that if we have y is equal to square root of x, getting the square of both sides of the equation will give us y square is equal to x, which is of course a parabola with vertex at the origin and it opens to the right. Of course, y square is equal to x, which is a parabola with a vertex at the origin and it opens to the right is this one. This is the graph of y square is equal to x. But we are considering only y is equal to square root of x. And please take note that if we have initially y square is equal to x, if we will get the square root of both sides of the equation, then that gives us y is equal to plus or minus the square root of x. And we're just considering the positive sign here, y is equal to square root of x. Now, if we will consider the graph of y is equal to square root of x, then we are just considering, okay, the values of y above the x-axis. So where y is greater than or equal to 0. So this red curve is the graph of y is equal to square root of x. And below, that is the graph of y is equal to negative square root of x. And as a whole, of course, it is a parabola opening to the right with vertex at the origin. So going back to the discussion on how to find the intersection of the curve y is equal to square root of x and the straight line, the vertical line rather, x is equal to 4, we can just do elimination by substitution. Now, If we have y is equal to square root of x, let us consider this as the first equation, and x is equal to 4 as the second equation. Considering the first equation, y is equal to x, we can replace or we can substitute x is equal to 4 in equation number 1, so that it will give us y is equal to square root of 4, and square root of 4 of course is 2. So we have a point of intersection at uh, 4, 2. This is the point of intersection. Okay, and if we will consider sketching the curve y is equal to square root of x, and the line x is equal to 4, and determine the region R. Okay, let us see, we can consider this as the y-axis. Okay, and let this be the x-axis. First, let us locate the point of intersection. The point of intersection is at 4, 2. So we call this point as the point whose coordinates are 4, 2. Make sure to label your graph. Okay. And at this point, you can now draw the line x is equal to 4. X is equal to 4 is a vertical line. This is the vertical line, x is equal to 4. And of course, if we will draw y is equal to square root of x, this is part of the parabola y squared is equal to x, where y is positive. So vertex at 0, 0. Okay, and intersecting the line x is equal to 4 at 4, 2. Okay, so this curve is the curve y is equal to square root of x. And we're actually considering this plane region R. This is the region R. And we need to find the volume of the solid generated by revolving about the x-axis, this region, bounded above by y is equal to square root of x, below by the x-axis, okay, and we have the line x is equal to 4. Okay, and make sure that you indicate always the axis of revolution by drawing circular arrow. So the x-axis is the axis of revolution. Now, you may also draw the solid, but it is not a requirement, okay, on my part. I am not going to require you to draw the solid. What I am going to require is to draw the element and the solid of revolution formed by the element, the appropriate element. Now, since you are considering the disk method, then the element must be drawn perpendicular to the axis of revolution. And the axis of revolution is the x-axis. Okay, take note that the first requirement is satisfied for the disk method. Okay, the uh, plane region R touches the axis of revolution. Actually, the x-axis is the lower boundary of the region R. Therefore, if we will use if we will draw the element must be perpendicular to the x-axis, the axis of revolution. So we have to use the vertical element. Okay, this is the element, and this point will have the coordinates x, y. And you can draw the element anywhere on the region. Okay, x, y is the point point of the on the element which touches y is equal to square root of x. Okay? Then try revolving this element about the x-axis. So if we will do that, okay, let's have the projection here, and we can draw the uh, circular disc. So we have the circular disc. Okay, just imagine that this is a circular disc. Okay, and going back to the rectangular element, of course, the distance of this point on the curve from the axis of revolution, from the x-axis, is y. And the thickness, of course, is the differential of x. And if we are going to rotate the element about the x-axis, we form this circular disc, okay, whose radius is the distance of the center. The center is on the axis of revolution. Okay, this is radius, the radius r. So we can see that the radius r is equal to the length of the element. And the thickness, okay, this is the thickness delta h. And delta h, the thickness, is equal to the differential of x. While the radius r of the circular disc is equal to the length of the element. It is equal to y. And to start, okay, with the solution of on how to find the volume of the solid generated by revolving y is equal to square root of x, the line x is equal to 4, and the x-axis, okay, we will consider, of course, the volume of the disk. And the volume of the disk is equal to pi r squared times the thickness, delta h. So since the radius is equal to y, the thickness is equal to the differential of x. If we are going to evaluate the integral of pi r squared times delta h from the lower limit a to the upper limit b, then that will give us the volume of solid of revolution. So the volume is equal to pi, okay, radius is equal to y, the thickness is, so we will have y squared. The thickness is the differential of x. This is actually the volume of the circular disc, okay, whose radius is the length of the element and whose thickness is dx. And if we are going to evaluate this, the integral, from the lower limit to the upper limit, of course, the variable of integration is x. Therefore, we have to consider the lower limit and the upper limit as the closed interval from 0 to 4. So lower limit of integration is 0, upper limit of integration is 4. And if we will evaluate the integral, of course, we cannot do it yet since the variable of integration is x and the integrand is in terms of y. Hence, we have to replace or express y in terms of the variable of integration x, so that it will give us volume is equal to the integral from 0 to 4. And since y is equal to square root of x, then y squared is equal to x. Okay, so, well, anyway, we have pi. We can write pi before the integral sign since it is a constant. Y is equal to square root of x. Okay, just get the square of the square root of x later times the differential of x. So this gives us pi times the integral from the lower limit 0 to the upper limit 4 of the square of the square root of x is x times the differential of x. And of course, we can easily evaluate the integral of x dx so that the volume is equal to pi times integral of x dx is x squared over 2. And we have to evaluate this from the lower limit 0 to the upper limit 4. But before we do that, let us factor out 1/2. So that volume will give us pi times 1/2. And we will evaluate x squared from the lower limit 0 to the upper limit 4. And this will give us pi over 2 times the value of x squared when x is equal to the upper limit 4 will give us 4 raised to the second power minus the value of x squared when x is equal to the lower limit 0. So we have 0 raised to the second power, okay, which will give us pi over 2 times 16, and 1/2 of 16 is 8. Therefore, the volume is equal to 8 pi cubic units. The volume of the solid of revolution formed by revolving about the x-axis, this plane region R, okay, is equal to 8 pi cubic units. Okay, so this is example number 4. We use this method. Okay, and now the second example is on deriving the formula for the volume of the sphere of radius r. Okay, now, of course, if we will consider the volume of the sphere of radius r, now our goal is to find the volume of the sphere. And the volume of the sphere, of course, is 4/3 pi r cubed, where r is the radius of the sphere. Now, we can do that by considering a semicircle above the x-axis, or you can consider also a semicircle to the right of the y-axis. Okay, let us just consider a semicircle to the above the x-axis. So let us see. Consider this as the x-axis, the y-axis, and of course the horizontal axis is the x-axis. And we are going to consider a circle whose radius is equal to r. Okay, of course, the equation of the circle is x squared plus y squared is equal to r squared when the center is at 0, 0. So just consider half of the circle. So we have a semicircle above the x-axis. Just imagine that this is a semicircle. It may not be perfect. Meron pa naman semicircle. Okay. And since we have a semicircle above the x-axis, the region considered is this region. And imagine revolving the semicircle about the x-axis. We can form a sphere, a solid sphere. And of course, the upper curve, okay, this semicircle, okay, can be expressed as y is equal to the square root of r squared minus x squared, okay, from the equation of the circle, where x squared plus y squared is equal to r squared. So if we will solve for y squared is equal to r squared minus x squared. And getting the square root of both sides of the equation, y is equal to the square root of r squared minus x squared. Of course, this must be plus or minus square root of r squared minus x squared. But since we are just considering the upper semicircle, y is positive. So we will consider y is equal to positive square root of r squared minus x squared. Okay, so this is represented by y is equal to square root of r square minus x squared, the semicircle. And the next thing to do, of course, is to draw the element. Of course, we can use this method since the region R, the semicircle, touches the axis of revolution, which is the x-axis. And since we will use the disk method, the element must be perpendicular to the x-axis. So the element must be a vertical element. So just draw the vertical element anywhere on the region R. Okay, this is the element, and this point, okay, on the semicircle is the point whose coordinates are x and y. And of course, the distance of this point from the x-axis, the axis of revolution, is y. And the thickness is the differential of x. Now, take note, we will rotate the region R, the semicircle, about the x-axis to form the sphere. And if we will consider um, the representative element, which is a vertical element, revolving this about the x-axis will form a circular disc. It will form a circular disc again. So let us draw the circular disc. Now I want you to show always the element revolve about the axis of revolution. So you have to draw the circular disc whose thickness is delta H, okay? And of course, delta H is equal to the length of the element. The length of element is y, and the radius of the disk is equal to, okay, this is the radius of the disk. It is equal to the length of the element. So the radius, uh, the thickness is delta x. Sorry for that. The thickness is delta x, or the differential of x, and the radius r is equal to the length of the element, which is equal to y. So again, we're going to start with the volume of the circular disc form. The volume of the circular disc is equal to pi times the square of the radius times the thickness. Therefore, if we will get the volume, no, of the circular disc of the representative element, then the volume is equal to pi, okay, r is equal to y, so y raised to the second power, and the thickness is dx. And if we are going to evaluate the integral from the lower limit, okay, the lower limit is negative r, this is negative r, and this is r, and upper limit, we are actually considering the closed interval from minus r to positive r. Therefore, the lower limit of integration is negative r, and the upper limit of integration is r. And again, there is symmetry with respect to the y-axis, right? The equation, of course, y is equal to the square root of r squared minus x squared is an even function. So there is symmetry about the y-axis, and the region R to the right of the y-axis is equal to the region R to the left of the y-axis. Therefore, the solid of revolution form on the right is equal to the solid of revolution form on the left of the y-axis. Therefore, we can also find the volume by evaluating the integral of y squared dx from 0 to r, but we will multiply it by 2. We will just consider the volume of the solid of revolution, okay, on to the right of the y-axis. So consider the quarter half of the semicircle, the quarter circle on the first quadrant, revolve it about the axis of revolution. Therefore, the limits of integration will go from the origin from 0 to r, but we have to multiply the integral by 2. So volume is equal to 2 pi times the integral of y squared dx from 0 to r. Okay, again, the variable rather of integration is x. Therefore, we have to express the integrand in terms of x, and the integrand is y squared. And y is equal to the square root of r squared minus x squared. Therefore, the volume is equal to 2 pi times the integral from 0 to r. Y is square root of r squared minus x squared. Okay, then square this times the differential of x. Hence, if we will simplify, then volume is equal to 2 pi integral from 0 to r of quantity r squared minus x squared times the differential of x. So we can easily evaluate the integral. Hence, we have 2 pi integral of r squared dx. R is a constant, is r squared x minus the integral of x squared dx, which is x cubed over 3. And we need to evaluate this from the lower limit 0 to the upper limit r. Hence, this gives us 2 pi, 2 times pi, times, okay, let us evaluate the integral, the indefinite integral r squared x minus x cubed r at the upper limit r. So we need to replace x by r. So that will give us quantity r squared times r minus r raised to the third power over 3, okay, minus the value of the indefinite integral at the lower limit 0. So when x is equal to 0, we have r squared times 0 minus 0 raised to the third power over 3. Okay, and of course, uh, the expression is equal to 0. Therefore, if we will simplify, we have 2 pi times r squared times r is r cubed minus r cubed over 3. And simplifying everything inside the grouping symbol, okay, we can get the common denominator 3. 3 times r cubed is 3r cubed minus r cubed. And simplifying further gives us 2 pi times 2r cubed over 3. So simplifying gives us, this is r cubed. Simplifying gives us 2 times 2 is 4. Okay, so we will have 4 pi r raised to the third power over 4. So this is the volume of the solid of revolution, okay, formed by revolving above the x-axis the semicircle whose radius is equal to r. So we have volume is, wait, it should be 4/3. Sorry about that. Okay, we have 4 pi r cubed over 3. Okay, or 4/3 pi r cubed, which is actually the volume of the sphere. The volume of the sphere is 4/3 pi r cubed. And we have here, okay, as a result of integration, we have volume is equal to 4/3 pi r cubed cubic units. We were able to derive the volume of the sphere of radius r by considering a semicircle revolve about the axis of revolution, which is the x-axis. Okay, as mentioned earlier, you can also consider uh, the axis of revolution as the y-axis. So you may consider a semicircle to the right of the y-axis. And you can form also the solid of revolution, the sphere. Okay, and let's have the third example using the disk method again. And in the third example, we will find the volume of solid generated by rotating around or about the y-axis, the plane region in the first quadrant bounded by y is equal to x squared. Okay, of course, y is equal to x squared is a parabola opening upward. Y is equal to 4 is a horizontal line, and x equals 0. Of course, x is equal to 0 is the y-axis. So the region R is bounded by the y-axis. So first we get the intersection of the parabola y is equal to x squared and the horizontal line y is equal to 4. So we will consider the system to get the points of intersection. We have to consider the system of equations y is equal to x squared and y is equal to 4. And consider this as equation number 1 and this one as equation number 2, and solve the two equations simultaneously by elimination by substitution. Since the first equation is y is equal to x squared, we can replace y by 4. We can substitute 4 in y, so 4 is equal to x squared. Or we can write this also as x squared is equal to 4. And if we will get the square root of both sides of the equation, then x is equal to plus or minus 2. But since we are just interested with the plane region on the first quadrant, then we will take x is equal to positive 2. Okay? And when x is equal, y is equal to 4, x is equal to positive 2. Therefore, the point of intersection is at 2, 4. This is the point of intersection of the parabola y is equal to x squared and the horizontal line y is equal to 4. Okay, and let us draw the region, the region R, and let us consider the y-axis and the x-axis. Let this be the x-axis. Now, when y is equal to 4, x is equal to 2. This is the point of intersection at 2, 4. And we can now draw the line y is equal to 4. Of course, it is a horizontal line. So this is y is equal to 4. And we can now draw the parabola. The parabola y is equal to x squared or x squared is equal to y is a parabola with vertex at the origin and it opens upward. This is the vertex at 0, 0. Okay. This is the origin at 0, 0. And we can now draw the parabola opening upward, vertex at 0, 0, and intersecting y is equal to 4 at 2, 4. Let us label. This is y is equal to x squared. And we are considering the region R bounded by y is equal to x squared, the first quadrant region. So first quadrant region, we don't need to draw the parabola to the left of the y-axis. Since we're just interested on the first quadrant area bounded by y is equal to x squared, the parabola, y is equal to 4, and x is equal to 0. Now, please take note that x is equal to 0 is the y-axis. And we're interested with this region R. Now, take note that the region R touches the axis of revolution. The axis of revolution is the y-axis. Okay? And since we are going to use the disk method, the element must be perpendicular to the axis of revolution. Hence, it must be a horizontal element. The horizontal element is perpendicular to the y-axis, the axis of revolution. And we call this point on the parabola as the point whose coordinates are x and y. And the distance of the point xy from the axis of revolution, okay, which is the length of the element is x, and the thickness, of course, is the differential of y. And since we will revolve the region R about the y-axis, then we revolve also the infinitely many rectangular elements about the y-axis. And considering this representative element, if we will revolve that about the y-axis, we can form again a circular disc. Okay, so let us draw the circular disc, whose thickness is delta H, and delta H is equal to, oh, sorry, there's no symmetry. Okay. Pardon with my drawing. So we have the disc. Okay, so whenever you solve for the volume of the solid of revolution, you have to draw the element revolve about the axis of revolution, and this is the radius r. The radius r is the length of the element. So the radius r is equal to the length of the element, which is x, and the thickness is the differential of y. And if we will set up the working equation, it will be based on the volume of the disk. Volume is equal to pi r squared times the thickness. Therefore, we have the volume is equal to pi. Okay, let us just write pi before the integral sign times the integral of, okay, r is x. So we will have x raised to the second power. The thickness is the differential of y. Okay, variable of integration is y. So we have to consider the closed interval from y is equal to 0 to y is equal to 4. So we are considering the closed interval from 0 to 4. Hence, the lower limit of integration is 0 and the upper limit of integration is 4. Now, we have to express the integrand in terms of y. And since y is equal to x squared, then we can replace x squared by y. And volume is equal to pi integral from 0 to 4 of y times the differential of y. Integral, of course, is y squared over 2. Integral of y dy is y squared over 2. Y squared over 2, and we have to evaluate this from the lower limit 0 to the upper limit 4. Okay, to make it simpler, we can just factor out 1/2. So pi times 1/2 times y squared at the upper limit 4 is 4 raised to the second power minus y squared at the lower limit 0 will give us 0. Hence, the volume is equal to pi over 2 times 4 squared is 16. Therefore, the volume of the solid of revolution, okay, is 8 pi cubic units. Okay, this is the volume of the solid generated by revolving about the y-axis, the region bounded, the first quadrant region bounded by y is equal to x squared, y is equal to 4, and the y-axis. So this is how to find the volume of solid of revolution using the disk method. So again, we have to remember two things if you want to use the disk method. The region must touch the axis of revolution. So meaning the axis of revolution forms part of the region. It is a boundary of the region. And second, the element must be perpendicular to the axis of revolution. And since the region touches the axis of revolution, any element drawn within the region will always touch the axis of revolution and perpendicular to the axis of revolution. And again, if we will evaluate or if we will find the volume of the solid of revolution using the disk method, okay, we have to consider or we have to base it on the volume of the disk, and the volume of the disk is pi times the square of the radius times the thickness. Okay, so this will be our basis. In our next discussion, we will consider the ring or washer method.